All right, now in this video, we're going to be looking at methods for solving quadratic equations. Now, there's at least 3 different methods that I would say that you can apply to solving quadratic equations. So one method would be factoring. Now, not all problems can be factored, but we will try to see if any of these are going to be the possible case. If factoring fails, another strategy you can use is the quadratic formula. And we'll definitely have to use, we can always use that even when it can be factored, but factoring doesn't involve square roots and fractions and stuff like that. So the algebra is a little easier if you can do the factoring. And then the third one is completing the square. Now, sometimes problems will be given to you in a form where it's actually like suggesting that you should complete the square, but because maybe the square is already completed. So we're going to try and follow each one of these for both of these problems, just so that you can see how they're set up in a way that suggests one method or another. Now, let's start with this first example. Now, can this one be factored? When it's multiplied out like this is really suggestive of the idea that, yeah, you probably want to factor this if it's factorable. Now, when you have leading coefficients like this, that can make factoring a little bit more complicated, but because the final constant is a 1, really all you have to worry about in a problem like this is, can this 3, does it have factors which are going to add up to 7? And I say add because this final constant is a positive. There is only one set of factors for 3, and that is 3 and 1. And 3 and 1 neither add nor subtract to give you 7. So this is actually not a problem that is factorable. There is no way to get that middle coefficient given the 2 things that you have on the end. So there isn't anything else to check, just 3 and 1 doesn't add up to 7. So we're going to move on then to the quadratic formula. Now, the quadratic formula is messy, but it will get us past this inability to factor. Now, recall that the quadratic formula here is going to apply to a problem that is in the form ax squared plus bx plus c equals 0. And that's what we have here, where a is going to be 3, b is going to be -7. The sign goes with the b, and then c is 1. So if we plug our stuff in, we're going to end up with we identified b as 7, but there's another negative in here. So just to be clear what's going on, this b is also -7. This a is 3. This c is 1. And this a is 3. So if I simplify, -7 times -1 basically is going to give me a 7. This -7 times -7 is going to give me 49. 4 times 3 times 1 is going to give me 12. And my denominator is going to give me 2 times 3 is 6. And then I need one more simplifying step at least. And that is 49 minus 12 is going to be 37. And I can't simplify that anymore. This is going to give me 2 solutions. One is going to be 7 plus the square root of 37, all divided by 6. And the other solution will be the same thing, but with a minus sign. Now, these are both real numbers. The square root of 37 is a perfectly valid number. If you put this in your calculator, make sure that you either add parentheses into your calculator or find a number for the numerator before you divide by 6. I get 2.18 approximately for the first solution, and for the second one, I get 0.15. They're both positive. 7, the square root of 37 is going to be bigger than 6, but not as big as 7 because this 36 is the 6 is a perfect square. 49 is 7 is a perfect square. So this is bigger than 6 point something. So there's still numbers left over, and then you divide by 6 and you get this fraction, which is a little bit smaller than 1/6 for the second solution. So but they're both positive, but they are real solutions. They're not integer solutions or rational solutions. They are real solutions. So there are values, but they're messy values. Now, the other way that we can go about solving this problem is completing the square. Now, completing the square, when you have a coefficient out front, can be a little bit tricky, but probably the easiest way to do it when you have an equation and you're not solving it in place is not merely to factor out the 3. It's simply to divide the entire equation by 3, because you do want to work with x squared by itself and not x squared with a bunch of other stuff. So I'm going to divide everything by 3, and that's going to give me x squared minus 7 over 3x plus 1 over 3 is equal to 0. Now, I'm going to move the 1/3, the constant, over to the other side of the equation, kind of get it out of the way. Now, when I'm completing the square, I'm trying to satisfy the equation x plus x minus a in this case, x minus a squared is going to be equal to x squared minus 2ax plus a squared. And so I'm looking at this portion of my expression. I have my squared term and my linear term. So I need to find the value of a. So essentially, that should be a squared. So essentially what I'm saying here is that negative 2ax is equal to negative 7/3 x. Oh, I can ignore the x's because I want to match the coefficients. So negative 2a is equal to negative 7/3. So I'm going to divide out the negative 2. And if I divide both sides by negative 2, I'm going to get a is equal to 7 over 6. So the negatives are going to cancel, and then I'm essentially multiplying by a half on both sides to divide by 2, and so I get the 7 over 6. Now, in order to get the constant that completes that square, I'm going to add a squared to not only the left side of the equation to complete the square, but also the right side of the equation. So my equation up here is going to become now 7 over 6 squared. And because I did it to the left side, I have to do it to the right side. And I can rewrite this expression on both sides. 7 over 6 squared is going to be 49 over 36. And on this side of the equation, I'm going to take my 49 over 36 and I'm going to subtract a third. So 49 divided by 36 minus 1 divided by 3. I would normally want to find a common denominator and so forth. But what this is essentially going to end up with in the end is 37 over 36. Now, again, the reason that we completed this square is so that we can rewrite this right side of the equation as x minus a. But our a was 7 over 6 squared is equal to, oh, sorry, it's not negative, is equal to 37 over 36. So now I have a perfect square on one side and I have some other number on the other side. I'm going to take the square root of both sides. Now, remember, when I take the square root as a process like this in solving a problem, what I have to deal with is the plus and minus part of this. The square root of 37 over 36. Now, the 37, I can't simplify, but I can take the square root in the denominator. And the square root of 36 is 6. So what I have now is this is equal to this. Did not copy the way I wanted it to. There we go. And now what I can do is I can add the 7 over 6 to the other side of the equation so that I can put all the constants together. So x is equal to positive 7 over 6 plus and minus the square root of 37 over 6. And since these have a common denominator, I can rewrite it as a single fraction, 7 plus or minus the square root of 37 over 6. The quadratic formula is derived from this process of completing the square. And so, of course, it gives us exactly the same answer. Great. So now that we have that solution confirmed by multiple methods, let's look at our second problem. Now, this problem is already in this perfect square form. So one strategy would be to take advantage of that fact and move the 24 over to the other side of the equation. And then square root both sides is equal to the square root of 24, but plus and minus versions, which require us to simplify. 24 can be factored as 4 and 6. 4 is a perfect square. The 6 will get stuck under there and the 2 will come out. And then we can subtract 3 from both sides of the equation, or add 3 in this case. If we add 3 to both sides of the equation, we get 3 plus and minus 2 square root of 6. That's probably the fastest way to solve this particular problem because it's already in this form. But that's not the only way that you can do this. So the other strategy that you could use is to try to factor or use the quadratic formula. But to do that, you would have to FOIL out this squared expression. So let's look at that. Recall that for FOILing, we gave the a minus x minus a squared formula earlier. But we're going to have to FOIL or apply the perfect square formula. And if we do that, we're going to get x squared minus 6x plus 9 minus 24 is equal to 0. And now I can combine like terms, x squared minus 6x, 9 minus 24. I think it's 15. Yes, negative 15 is equal to 0. Now we could try factoring, although given the fact that we got a square root on the previous method, I don't think it's going to work. But let's work through the reasoning here. We have a leading x squared, so I only have to worry about factors of 15. 15 has a minus sign in front of it, so I need factors of 15 that have a difference of 6. So what are my factors of 15? I have 1 and 15. That is a difference of 14, not 6. And the other combination is 3 and 5. That's the only other possibility, but that has a difference of 2, not a difference of 6. So this is not factorable. And so we apply our quadratic formula. Our b is negative 6. We put that in. Our a is 1. And our c is negative 15. Again, remember to take the sign with you. Now, negative times negative 6 is going to give me positive 6. And then negative 6 squared is going to give me 36. And negative 4 and negative 15, the one's obviously not going to do anything, is going to give me plus 60. And the denominator will just be 2. 36 and 60 going to give me 96. Is divisible by 16. 96 is 6 times 16. So I can take the square root of 16 and pull that out as 4, because the square root of 16 is 4, and then leave a 6 behind. So 4 comes out, 6 stays behind. And then remember, I have to divide both of these terms by 2. So this is going to give me x is equal to 6 divided by 2 plus and minus 4 square root of 6 divided by 2, which 6 divided by 2 is 3, and 4 divided by 2 is 2. And then the square root of 6 is left behind, which is, again, the exact same answer that we got when we were using the completing the square strategy, since the square was already completed. So same answer, and again, they're derived from the same process, so of course you're going to get the same answer.